Okay, here we have a problem where we're talking about medicine. The half-life of a radioactive substance is the time it takes for half of the material to decay. A hospital prepares 100 milligram supply of technetium 99M, which has a half-life of 6 hours. So what that means right there is if I've got 100 milligrams and there's a half-life of 6 hours, that means in 6 hours, my 100 milligrams will be reduced to 50 milligrams. 6 hours later, that 50 milligrams will be reduced to 25 milligrams. So you can see here in the table, you've got the time elapsed, you've got 6 hour intervals. So the first 6 hour interval, 6 hours later, 100 to 50. Another 6 hours later, you'll be down to 25. Another 6 hours later, down to 12.5, and so on and so on and so on. Now, technically, according to this model, 100 milligrams will never, ever, ever become zero because you'll always have a small amount cut in half, cut in half, cut in half. It will become, at some point, negligible, but in all intents and purposes, there will still be something left because there will always be something to cut in half. So here we have the half-life of the radioactive substance. That means the amount that we lose is 50%. The amount that we retain is 50%. So let's remember that we have y equals, we have an initial value, and we're going to take that initial value and we're going to multiply it by the percent remaining. And then we're going to raise it to the x power. And this is, in this case, it's going to be time. Or it could be intervals. Okay? So, we're going to write an exponential function to find the amount of technetium that remains after 75 hours. 75 hours is not going to be a 6 hour interval. It's going to be somewhere in between. So we're going to start with y equals, the initial value is 100 milligrams. The percent remaining would be 50% raised to the x power. Y equals 100 times 0.5 or 1/2 raised to the x power. Now, if x equals the number of intervals, but we need a partial interval, we're going to have to take that x and we're going to have to divide it by 6. So for instance, if I have 6 hours, 6 over 6 would be 1 interval. If I have 12 hours, 12 over 6 would be 2 intervals. So if I have a partial interval, that's why I need to divide by the 6, because not everything is perfect. So we're going to have x divided by 6. And that's going to be an exponent, and it doesn't quite look like an exponent. So we're going to come back up here, and we're going to make that an exponent. And that will be our formula. That's going to be our formula. So I'm going to keep that in blue. And now I'm going to use that formula to find the amount that remains after 75 hours. So y is equal to 100 times 1/2 raised to the 75 divided by 6 power. So 75 divided by 6 is going to be approximately, we'll put that into our calculator, 100 times 1/2 raised to the 75 divided by 6 power. You should get 0.017 milligrams remaining after 75 hours. Let's do another one and make sure we've got this. Phosphorus is used to study a plant's use of fertilizer. It has a half-life of 14.3 days. Write the exponential decay function for a 50 milligram sample. Find the amount remaining after 84 days. And now I'm going to define my variables. So I've got y equals a 50 milligram sample to start with. Half-life means 50% or 0.5 remains. And then I'm going to raise that to the x over 14.3 days, or just x over 14.3. So x is going to stand for the number of days. After the initial sample. And then y is going to stand for the number of milligrams remaining after x days. So if we want to find after 84 days, we're going to be able to put that 84 in. We get 50 times 1/2 raised to the 84 divided by 14.3 power. Let's write this a little bit more clearly. 84 divided by 14.3 power. Now in our calculator, we're going to enter it like this. Y equals 50 times parentheses 1/2 or 0.5 upper caret, and then parentheses 84 divided by 14.3. When we put that into our calculator, we get approximately 0.852 milligrams remain after 84 days. Okay, so be sure that you are defining your variables. Be sure that you're writing the function. That's not the function. This is the function. Be sure that you're writing the function with an input and an output. Then show your work as to what you're putting in for that x value to get your answer of 0.852 milligrams. Okay, you go ahead and try this problem, and I will come back with the answer. So press pause, and then be sure to show all your work, show all the definition of your variables, your function, and your final answer. And then press play when you're ready to reveal. Okay, welcome back. We have a function of y equals 200 times 1/2 raised to the x divided by 8.14, where x is equal to the number of days after initial sample. Looking for the right wording. And then y is equal to the number of, this is measured in milligrams, number of milligrams of iodine after x days. So we've got our variables defined. We've got our function. defined. And now I'm going to use that function to find how much remains after 72 days. We put a 72 in for x, and you should get approximately 0.435 milligrams. .435 milligrams. Okay, let's try one more. Go ahead and press pause and see if you've got this next one. Be careful of the millennia. So be careful that you're reading the problem. Press pause. Be sure to read the entire problem. Get your units. We're talking about millennia versus years. And then come back and check your answer. Okay, welcome back. I've got an answer for you. I've got y equals 24 times 1/2 raised to the x over 5730 power, where x is measured in the number of years after artifact is found. No, after the artifact is, after the artifact not after it's found, after the artifact is initially created. I don't know. I guess that's what you would say. An artifact is created, came into existence, and y is going to be the number of, is it milligrams again? We just love milligrams. Milligrams of carbon 14 remaining after X years. So number of years in age, maybe, of the artifact. Yeah, I like that better. The number of years in age of the artifact. I think that makes more sense. Then we're going to put our value in. We need 30 millennia. So 30 millennia would be 30,000 years. So you put 30,000 divided by 5730 into the exponent, and we get approximately 0.637 milligrams. That is how many milligrams of carbon 14 that remains. Okay, in the next video, we'll do a little bit more graphing with the value of E.